Hi there, welcome back. Now, in this third lesson, we start speaking about extremes, and we will introduce extreme value theory. Obviously, very shortly, because extreme value theory is an extremely important branch of statistics that I personally like a lot, but it can be the topic of several courses if you really want to enter into the details, into the mathematical proofs, and into the little modeling of all the exceptions that we can actually encounter. Now, in this course, we will just introduce what we need, the basics of extreme value theory. If you are interested, I hope you will then continue and you will go deeper into the understanding of this fascinating field of statistics. Now, what we want to do is to be able to play with extremes. We will see that for us, extremes are the maxima or the minima, because we will essentially focus on the maxima in what we will say, because remember that we are considering the loss distribution, and for us, losses are positive. So since we want to avoid large losses and we want to be able to model and hedge large losses, we will focus on the maximum. Conversely, if you are interested on very large profits, that in any case for us are not a big risk, they are actually something that we hope to see, in that case, you should focus on the minima. What we will say for the maxima is essentially holding also for the minima. It's just a matter of changing the sign. And in fact, very often when you model a distribution which has two tails, the left tail and the right tail, what you can do is to first model one tail and then the other by reflecting the observations. So a very common way of modeling, for example, the left tail, when the tail goes towards minus infinity or negative values, is to flip the tail to make it positive, model the maximum under that flipped tail, and then come back by a change of sign. Now, what we will see is that extreme value statistics is this important branch of statistics that deals with the modeling of minima and maxima and their probabilities. Okay, we will see that using EVT, extreme value theory, we will be able to better compute quantities like the valid risk or the expected shortfall under specific assumptions for what concerns the behavior of the tail of the distribution of the losses. We will see that in extreme value theory, there are different ways to define a tail. We will define tail classes, we will define the maximum domain of attraction, and other important concepts. What I would like to stress is that what we will consider together are extremes. For us, extremes are a specific type of event. Extreme value theory focuses on these events, so it does not care about all the events that are more related to the bulk of distribution, that is to say, those events that tend to be closer to the mean, to the median, to the center part of a distribution. What is important for us is actually what happens in the tails, so far from the mean, far from the median. And in fact, you will see that very often we will focus, for example, on the top 5% of the losses, and even less, like the top 1% or the top 0.1%, because these are for us the game changers. So we are obviously interested also in modeling the small losses, because many small losses nevertheless can have an impact. But when we use extreme value theory, we are just focusing, we are zooming in on the very large losses. So we will not take into consideration losses of a few thousand euros, but we will look for million and billion losses. Okay, let's start by considering a very, very, very important distinction. That is the distinction between outliers and extremes. Unfortunately, a lot of people tend to use the two terms as synonyms, but this is a quite big error. An outlier and an extreme are two different things, and the modeling approach is completely different. So it is very important to understand what an outlier is and what an extreme is. I'm pretty sure that actually in your mind somewhere there is the distinction between an extreme and outlier, but I also believe that it's important to clarify that because, at least for us in extreme value theory, it will be a fundamental distinction. Okay, so what is an outlier? I think that the best way to describe what an outlier is just to look at the word itself. Outlier. An outlier is something that lies outside. Outside of what? It is something that is out of the natural range of variation of the phenomenon that we are studying. Now, what does it mean out of the natural range of variation? An outlier is a value that is so big or so strange not to belong to the object of our analysis. So it is like I'm measuring the height of people, okay, in my classroom or everywhere, I'm measuring the height of people, and all in a sudden, one of the measurements is something like 12 meters. Now, we all know that 12 meters is something impossible in terms of human height, okay? So this is a very simple yet effective, I hope, example. What we will see together is that when we have an outlier, when we have an observation that we can safely define as an outlier, there are solutions that include either trying to correct the observation or to remove the observation if we are not able to make any change to the value of the observation itself. In fact, what is relevant to stress is that typically an outlier is nothing more than an error of measurement or a problem of reporting. So maybe the measurement was correct, but then it was reported in the wrong way, like forgetting a comma or a dot or whatever, as we shall see in a minute. Now, if we consider conversely an extreme is an event that is characterized by two specific features. It is extreme in terms of magnitude. So an extreme is an event that is very large or very small. So if it is very large, so it's big, it will be a maximum. If it is very, very small, it will be a minimum, okay? Remember that in extreme value theory, we can be interested both in maxima and in minima. We will mainly focus on maxima, but there are also situations in which one might be interested in minima. So an extreme needs to have a particularly strange, unusual, large magnitude, where large needs to be, large needs to be taken as meaning very, very large, very, very big, or very, very small, okay? The second characteristic is the fact that an extreme event needs to be rare. So it needs to be an event that we do not observe regularly. It's something that rarely manifests itself, okay? So an extreme event for us is something that is extremely large and rare. When we are in front of an extreme event, then we can use, for example, extreme value theory. As we shall see later, even if they are very tricky objects, we can also introduce a third type of event that are rare events. A rare event is an event that is rare, so there is no particular connotation of magnitude. We are not saying that it is very large or very, very small. It is just something that we rarely observe. That is a rare event. What is an example of rare event? A typical example is, for example, a genetic mutation. A genetic mutation is a rare event, and it may happen that this mutation has no particular big impact, okay? So in that sense, we can focus on the rare event without any connotation of about the magnitude, about the size of the event. It goes without saying that all extreme events are rare events, but not all rare events are extreme events if we follow our definition. Also, from a modeling point of view, the way in which you approach extremes and rare events is different. We will see that in extremes, for extremes, we have results like the Fisher-Tippett theorem, like the Pickens-Bachmann, the Hahn theorem. For rare events, you usually use point process approaches and other statistical tools. Now, let's consider a very simple example. Imagine that I'm measuring the height of people in a group, okay? Now, on your screen, you see this little table with the height of people expressed in meters, and we have Mark, we have Sue, we have Tom, we have Jane, and so on, and we have all their heights, okay? Now, imagine that I'm studying this data, so I want to make an analysis of this data, and I observe someone that is 2.15 meters tall. Now, is this an extreme or an outlier? Unfortunately, a lot of people would say an outlier, but this is not an outlier. So 2.15 meters is something that we can observe. We know that is a value that exists in the range of variation of the height of people, okay? It's for sure not a value that we observe very, very often. So, but also there, it depends on the type of population that you are considering. If you consider people playing in the NBA, then this value is no longer so rare and so unusual. So one thing that I want to stress is that the definition of extreme is, but if you want also the definition of outlier, is always very dependent on the phenomenon that you are studying, on the definition of the phenomenon that you are studying. Because one thing is to say I want to study the height of the human population, and one thing is to say I want to study the height of basket players, okay? So what might be an extreme for the human population can be a quite standard value for what concerns the NBA population. But in any case, given the definition that we gave of extreme and outlier, 2.15 meters is for sure an extreme and not an outlier, okay? So let's consider another measurement, and we find someone who's 1.42 meters tall. Question, is this an extreme or an outlier? Again, for sure it is not an outlier because we know and we have observed a lot of people even smaller than that. So for sure it is not an outlier. Is it an extreme? Probably yes, but is also not so far from the median and the average if we consider the world population. For certain countries, maybe it is actually an extreme, but for other countries, not necessarily. So we should really have a look at the data to try to understand if it is really an extreme or something that we can still consider being part of the bulk of the distribution. But for the moment, we don't care. So let's say that if we have to choose between outlier and extreme, this is more likely an extreme and not for sure an outlier. Then we observe someone that is 4.7 meters tall. As the example I made a few minutes ago, in this case, we can safely say that this is an outlier. Why? Because both medicine and biology tell us that it is not possible to observe a human being this tall. For example, looking a little bit at the literature for what concerns the human height, I found out that there are biologists that believe that in principle, we could observe someone that is 3 meters tall and even something more. But then for physiological reasons, our body will not be able to have someone taller than that. So there is a sort of upper bound to the height that a human being can reach. But in any case, according to both medicine and biology, 4.7 is not a value we can expect. So we can say that this is actually an outlier because it lies outside of the range of variation of human height. And then we observe someone who's 0.56 meters tall, so 56 centimeters. The question is this an outlier or an extreme? Now, I'm pretty sure that many will tell it's actually an outlier. It's almost, so it's something that cannot be observed. I'm sorry to contradict you because actually the smallest man in the world was smaller than this. If I remember correctly, was something like 54 and something. So 56 centimeters is a value that lies within the range of variation. I totally agree with you that this is extremely rare, so it's not something that we observe every day. Nevertheless, if you look at the number, at the frequency of this type of observation, so the number of people that are shorter than 1 meter, you will find out, to your big surprise, that their number is larger than what you might think, because we tend to make inference on the basis of what we observe every day around us. But there are places in the world in which the average height is definitely smaller than, for example, what I can observe in Switzerland or what I can observe in Italy, and for sure what I can observe in the Netherlands. So if I consider myself, in Italy, I'm taller than the average. I'm definitely taller than the average. In the Netherlands, I'm exactly in the average. Okay, so again, everything is very relative. What I want to stress is that all this idea of having objective measurement and objective definitions for phenomena, at least for me, it's a little bit pretentious. There is always a very large degree of subjectivity in all the analysis that we perform. This does not mean that all the results that we get are useless because there is a degree of subjectivity. Until you can convince people that your assumptions are correct, until the method that you are using is correctly developed and used, then the results you will find are very, very useful. And they can be shared with others, they can be discussed. But thinking that the little number you obtain from your method is the truth, again, as I told you in the first class, is extremely risky in risk management. Okay, so this is, for example, a way of looking at extremes and outliers if we consider the height of people. So let's consider a financial example now. As you can read on your screen, there is a bank that is looking at the percent losses and profits it has experienced on loans in the past 5 years. Okay, for a given client, double X, it observes a loss of 20%. Now, this is essentially a relevant loss, is a 20% loss. Here, remember that for us, again, positive quantities are losses, so 20% is a loss. Okay, 20% is for sure important. I will not even say extreme, but yet, if we have to simplify and just choose between extreme and outlier, I repeat, this is an extreme, are not an outlier. If we consider a loss of minus 4%, that is to say a profit, for sure is not neither an extreme nor an outlier. But again, if we have to choose between the two categories, then it is for sure an extreme and not an outlier. If we observe a loss of 81%, it is definitely an extreme and not an outlier because it is possible. If we observe a loss of 170%, conversely, we can somehow safely say that this is an outlier because losing more than 100% on something, we will see that when we consider credit risk, we define quantities like the exposure at default and the loss given default. And the loss given default is the percentage of the exposure that we have at the time of default of a counterparty that we actually lose after the recovery process and all the things that we will discuss together. There are situations in which, if you consider costs like the legal costs that you might have for the recovery process and administration costs and all the other things, you may end up with a counterintuitive loss given default, which is larger than 100%. So you lose more than what you were supposed to lose initially at the time of default of your counterparty. Yet, if it is more, it can be 101%, 102%, but 170% is for sure something that we can somehow safely say it is not possible. So it can be categorized as an outlier. For what concerns profits, on the contrary, we observe 81%, so a loss of minus 81%, a profit of 81%. Now, here the discussion if this is an extreme or an outlier can be quite interesting. For example, since we are speaking on losses and profits on loans, okay, that you as a bank has given to some of your clients. Now, 81%, a profit of 81% in many countries will not be possible because it would be against the law for usury. So a profit of 81% on a loan could be usury, and depending on the legal framework of your country, it is very likely that this is actually an outlier. So maybe the real value was 8.1 and it was mistyped, and so it was registered as 81, okay? How we correct for an outlier? As I told you, one of the big differences between an outlier and an extreme is that we correct for outliers. We do not correct for extremes. Now, how do you correct for an outlier? There are different ways for doing that. If you can directly correct the observation. So imagine that you are observing the height of people, as in our previous example. At a certain point, I see that on the second row, I have 169, and all the heights of people are expressed in meters. So what I can assume somehow safely, and in any case, this value will not change the result of my analysis, that would be robust if I'm interested in the average height of people with respect to one of these values. I can think that maybe my collaborator, my friend, my colleague, whatever, just forgot to write down the dot. So the value is not 169, but it can be corrected to 1.69, okay? This is what we call direct correction. Now, another way of correcting observations is to average. This is something quite common, for example, in time series, as we shall see. Now, imagine that I'm measuring the average temperature in a given city, okay? In day 1, I observe 20 degrees. In day 3, I observe 26 degrees, and these are Celsius degree, okay? And then on day 2, I see that there are 72 degrees. Now, 72 degrees is for sure something that is not possible unless you want to cook the population of a given city. Okay, so if you want to slow cook someone, 72 degrees is more than okay. But in nature, this is something that we do not observe if we are looking at the temperature in a specific geographical area. So what we can do, we can safely remove this observation, 72, and if there is no other measurement or is not possible to obtain an alternative measurement, and we don't want to leave an empty cell in our time series, Sometimes we can do that, and we can still play with a time series with some missing values. It's not a big deal. But if we want to have a value, what we can do, we can take the average value between the two closest observations, that is to say 20 degrees and 26 degrees. Okay, that can be something that we can do. In other situations, it can be difficult to correct. And in those situations, for example, I can remove. So I will remove the observation from my data set because I'm not able to find a way of correcting the observation. Now, how can we detect outliers? Statistically speaking, outliers tend to lie outside the range of variation. So in any case, in terms of magnitude, would be different from what we can usually observe. But differently from an extreme, they are impossible with respect to the phenomenon that we are observing, while an extreme is something that is far from the median, from the mean, but it is possible. Okay, to find outliers, there are many different ways. So first of all, you can try to look for the observations that are far away from the bulk of the distribution, and then you can use box plots, you can use PCA, you can use a lot of tests like the chi-square plots, Bayes test, and so on. You can use rules of thumb that are usually working with respect to ranges and interranges. So there are different ways of doing that, but the most important thing, the very important thing, is that in order to safely play with outliers, you need to have an understanding of the phenomenon you are trying to model. Not to confuse an outlier with an extreme, you have to know what you are doing. You have to know what you are analyzing. So your knowledge of the phenomenon is pivotal. So if you are a statistician analyzing medical data for the first time, if you're a statistician analyzing financial data for the first time, and you are not an expert on that type of data, the best thing you can do is to ask for help, to ask someone that knows the stuff to help you grasping and understanding the basic characteristics of the phenomenon you are studying. Otherwise, you can really make a lot of errors. And, for example, considering an extreme an outlier and removing the extreme from your dataset is a quite important error. Not only in risk management, but in general. So very often I see people plotting regression lines to closer points, and simply because one point is not in the cloud as they think it should be, they remove it. When it is a totally plausible observation that was correctly measured and observed in the reality of things. But since that observation does not follow the model they have in mind, then the problem is the observation. No, the problem is your model, okay? Please recall that the problem is always your model, is not reality. It's the way in which you want to approximate reality that can be a problem, not reality itself. If we can correct or remove outliers, how we correct for extremes, I already told you, the answer is that we do not correct for extremes. There are different things that we can do with extremes. For example, we might decide to model extremes together with all the other observations, so to model the tail together with the bulk of the distribution, or we can just focus on the tail, so to separate the bulk of the distribution from the tail. But to separate and analyze independently, and then obviously at the end, putting back together the results, is different from removing and ignoring. That is what you have to do, for example, with outliers, if you are not able to correct them, okay? So this is very important. So I think that if you want to fail an exam on extreme value theory, what you can say is that you correct for extremes and that you remove the extreme of observations, which is unfortunately what many scholars do, and something that, at least for me, it's really painful. We will see that depending on the type of extremes, and later in this lesson or in the future lessons, you will see that we will give different definitions of extremes in terms of their tails. So we will see that when we have a phenomenon, we can study the tail of the phenomenon, and this tail may belong to different families, to different classes. Depending on the class, we can say what type of tools are better used. But without even introducing the classes for the moment, we can say that we can distinguish three main situations. Okay, then obviously the lines between the different situations are a little bit blurred, but to simplify, we can say that there are three situations. The first situation is when we are considering extremes, that is to say minima and maxima that belong to a non-risky phenomenon, so whose impact for us is not particularly strong, so maybe losses, but not extreme losses, that is to say losses that are in terms of size manageable for us in terms of our capital, in terms of our risk management setting. So if we are considering a phenomenon that is bounded, for which the support of the distribution that we are considering to represent the randomness of the phenomenon, in which the support is finite, an example, the uniform distribution on 0, 1 or 0, 10, or the beta distribution. So if we are considering a phenomenon that is bounded and non-risky, then the standard statistic that we know from the basic courses we had is more than sufficient. So we can play with the mean, we can play with the variance, we can build confidence interval. Normality works and can be used to study and to approximate all the different things we might be interested in, so no big deal. There is then a second class. A second class is the class in which the minima and the maxima belong to an unbounded phenomenon. So the range of variation of the phenomenon is, for example, between minus infinity and plus infinity, and yet the phenomenon is non-risky. So for example, we know, or let's assume that we have that the losses of our portfolio are normally distributed. Now, normal distribution goes from minus infinity to plus infinity, but the mass decays very quickly. So we know that observing something that is larger than 4 times the standard deviation with respect to the mean, or 5 times the standard deviation, is so rare that we can assume its probability of happening almost 0. Okay, so if we are in this setting in which we have an unbounded phenomenon that is nevertheless non-risky because the large deviations that we can observe are not so large, and the very large deviations have a mass which is almost 0, then in this situation, we can use a combination of the standard statistics that we know from our basic courses and some tools from extreme value theory. Then there is the last category, which is the one that we can call the catastrophic category, so the one of the catastrophes, in which we are considering a phenomenon that is unbounded and risky, so that can generate very, very large losses, very, very large profits. But again, for us, profits are not a problem, but in any case, we can observe very large variations with respect to the phenomenon. And when the phenomenon is unbounded, this is for sure very, very risky. But there are also situations, as we shall see, in which the support is bounded. So there is an upper bound, for example, but the upper bound is so big and so far away that still the losses that can be generated by the phenomenon are extremely risky. And even if there is an upper bound, we might be inclined, by looking at the data, if we ignore the characteristics of the phenomenon, and again, we will be back on that, but it's always very important to notice that, we might be inclined to think that the phenomenon is unbounded, when it is not. So imagine that you are interested in modeling the number of casualties in armed conflicts and wars. Okay, this is a work that I performed together with Professor Nassim Taleb. Now, if you look at the number of casualties in the different wars, the Second World War, the First World War, the French Revolution, the Civil War in the US, and all the wars we can think of all over the world, you will find that the distribution of casualties is extremely fat-tailed and extremely risky, and it can generate very, very large observations. Think of the Second World War that killed, depending on the historical source that you use, between 40 and 80 million people. So we are really speaking about very large numbers. Okay, if you look at the data, I will show you that you might be inclined to think that you are looking at a phenomenon that is extremely, extremely erratic, up to the point that the theoretical distribution that could represent the phenomenon does not have a finite mean. So you're really considering something that can generate an infinite number of casualties. But then you know that this cannot be the case actually, because if we are considering wars, we are considering the human population, there is no single war that can kill the entire human population. Or even more, there is no single event that can kill more than the world population. So there is an upper bound. And the fact that there is an upper bound immediately tells us that the moments of the distribution need to be finite, because if there is an upper bound, moments are finite by definition. Now, why I'm making this example? Because this is the typical example in which if you ignore the existence of an upper bound, because it's almost impossible to observe in our data a conflict that killed the world population, and remember, at least one person, and if you want, I will play the role, needs to be alive to collect the data and to analyze that. So if you want, I can do this dirty job of being the only survivor, but you need at least one person, okay, if you want to perform the analysis. And in any case, even if that person dies, you can kill at most the entire world population. So there is an upper bound. And ignoring the upper bound can lead to misleading interpretations of your results. So again, I stress it's very, very important. It's fundamental when you study something that you try to think about the basic properties of the object you are studying. It is like now when you see all those models for the modeling of pandemics, like the COVID-19, and essentially they make extrapolations such that after 10 days, the entire world population would die, okay? Or even more than the entire world population. Okay, then we can question, we can ask ourselves if such a model is really reliable or not.